Hi, my name is Narek, a PhD student at University of Grenoble Alps. I will be presenting Federated Self-Supervised Learning in Heterogeneous Settings, Limits of a Baseline Approach on Human Activity Recognition. This study was done with Dr. Romain Rambaud, Professor François Potet, and Professor Philippe Lalanda. Federated learning was introduced as a distributed learning framework where learning happens closer to the data. In the usual paradigm, we have a server that distributes a model to all clients where on-device training is happening. With this paradigm, we gain enhanced user data privacy. It was proposed by Google back in 2016. Adapting federated learning into the pervasive domain isn't quite obvious, because the original motivation of federated learning was a privacy-oriented meta-learning method where we wanted to have better performance of the server model by having it train on client's data. So in our case, where we want to have better performance on client, there needs to be a shift from a server-centric one to a client-centric goal. More so, federated learning has generally been studied on supervised learning tasks with labeled data, but labeling is quite expensive. And when we adopted learning into the actual edge devices or small devices, we really need to take into account the resource constrained environment, and it needs to be elaborate on how it can be taken care of. The purpose of our work is to remove this doubt. Precisely, we try to answer the following research question. Can the vast unlabeled data at the edge be leveraged? Are self-supervised learning methods such as the autoencoder able to take advantage of the unlabeled data? How do we better capture knowledge in a federated learning way? Is the autoencoder sufficient in the same sense? And we see it more as a baseline in our study. The framework of federated learning usually happens as so. We start with a server sending a model to multiple clients, in this case here, which are smartphones. These clients or smartphones perform on-device training with the given model with their local data, whether labeled or unlabeled. This personalized model that captures the knowledge of these users' devices is sent back to the server. The server combines these personalized models to create the next generations of the server model. And this steps happens again for the next round, where 1 to 4 steps is called usually a communication round. What's unique about this paradigm is that no user data is ever communicated. We're only dealing with details of the models or the model directly. Below are the challenges we specifically look into when adapting federated learning into pervasive applications. The lack of labeled data limits our domains and usage. Users generally do not favor to label their own data. They usually do not have the incentive to do so, and at times, labeling data requires expertise knowledge in the field to obtain the correct and accurate label. And when we try to bring the experiments out of simulations onto real devices, we must really design our architecture with respect to the device computation power and memory capacity. And when dealing with real users, we must respect storage and communication cost requirements. More so, as in any collaborative learning problem, we deal with the problem of non-IID data, where it stands for non-independent and identically distributed data, which in our case means that a single user's data is not at all representative of other clients or subjects. And this could be caused by different usage or differences in sensors. It's one of the biggest obstacles for collaborative learning techniques, which of course includes federated learning. From the previous race marks, we make the following learning environment assumptions for our experiments and tests. Clients do not have any labeled data. They do, although, have many unlabeled data. And the server, on the other hand, have a proportionally smaller amount of labeled data compared to the amount of unlabeled data at the clients. Clients have an onboard computation and memory budget we must respect, so we cannot use something that's computationally too complex. The learning architecture we use is the autoencoder, or AE for short, or the goal of the autoencoder is to reconstruct the input signals after compressing it into the latent space, which we see here. It operates with two core mechanisms, which is the encoder, which is in charge of extracting meaningful features and compressing them into this small latent space, which has meaningful representations, where the decoder tries to take the data from the latent space here and trying to replicate as best as possible the same image from the input. So here, the encoder is trying to learn features as accurately as possible, or to able to represent them into meaningful, summarize them to meaningful features into the latent space. And we can translate this architecture into a classification task by removing the decoder section here and adding a classification head, as you can see in this image, for classification purposes. And what's happening here is happening in a self-supervised learning manner, where we don't need any label data. As you can see here, we only need the input without its label. And the architecture is very lightweight compared to alternative self-supervised learning approaches, which is ideal for our case on edge devices. So we do our experiments in the domain of human activity recognition on smartphone. This is interesting to us because activities have shared generic patterns which can help one another collaborate in learning, but they're also very highly idiosyncratic. So this means that the way a person, for example, the way a person walks is different from another way a person walks based on their difference in gender, age, or even culture. And we evaluate our experiment on a pool from 4 different data sets, which in total have 13 unique activities and 80 clients. And we upsample and downsample the clients from different rates so that everyone has a sampling rate of 50 Hertz. And we use a window of 128 and an overlap of 64. And we do 200 communication rounds of federated learning in a self-supervised manner. Below is the architecture of the autoencoder, which we adapted from another study for our use case. It mainly comprises of 4 convolution layers in the encoder and 4 convolutional layers in the decoder. The 4 dataset we use for our learning environments are the UCI dataset, which is small and homogeneous, which contributes 5 clients. It's a famous benchmark dataset. And we have the heterogeneous human activity recognition dataset, the HHAR dataset, which has 51 clients and is systematically heterogeneous because it comprises of multiple different devices in the data collection. And we have the real-world dataset, which is a bit large compared to the other two, and it has 15 subjects that are a bit diverse in terms of age, gender. And we have the Sussex Hallway Locomotion Dataset, or the SHL, which has the biggest dataset compared against the other three of 9 clients. And uniquely, they have a locomotive class such as car, bus, train, and subway, bike. So for each dataset, we have the following partition, where for each subject of each dataset, we take 20% of the subject's local data as the test set, and the remaining 80% we consider as the train set. So from this train set, 20% of the train set, we take their data with their labels and use them as the label data at the server for the fine-tuning stage. And the remaining 80% of unlabeled data remains the client, where here we use for the self-supervised training with the autoencoder. So putting together the use of the autoencoder architecture into a federated learning framework, We end up with the following learning pipeline, where we start again with the server model, propagating the autoencoder to all different clients, and all these clients would perform local self-supervised training on their local devices. Once done with the training, they would aggregate the model to the server, and this is done as previously stated for 200 communication rounds repeatedly. And once done, we remove the decoder layer and we attach the classification layer, where we do the fine-tuning stage on the only on the label data of the 20% of each subject. So extending the pipeline we presented, we actually came up with two other configurations as an evaluation setup to compare against the federated learning plus autoencoder approach, which we termed the previous pipeline framework here. And the other approach we came up with for comparison is the conventional plus autoencoder approach, where where the autoencoder is just learned in a conventional way, where all the unlabeled data of the clients here are pulled together. So here we can compare against the FL plus autoencoder approach to see if the aggregations in federated learning was able to aggregate the different clients, all 80 different clients together well. And so once the autoencoders learn on unlabeled data, the decoder is taken off again, and we again do the fine tuning on the labeled data. The other approach is the simple conventional approach, where there's no self-supervised learning. We just train on the small amount of labeled data. We want to know if the autoencoder feature training actually adds a benefit to the classification tasks we have at hand. So this slide reports all the performances we had for the three separate configurations. First off, starting with the federated learning plus autoencoder approach, we're able to see that it's able to converge as more communication round goes on, rather than diverging. This means that all the 80 clients is able to get better in extracting features, and it's able to improve as the round goes on, and it's able to aggregate with other clients rather than diverging. And in terms of the classification performance, here, while looking at the table, we're able to see that the conventional approach, which only trained on the label data without the autoencoder feature learning, is able to be the best in performance. So this really tells us a big story about the feature learning abilities of the autoencoder. So first off, the process of learning on the autoencoder is quite expensive, since we're learning on a lot of unlabeled data, and it's actually quite shocking to see. Quite interesting to see that there was actually no gains in performance at all to have to even have gone through that lengthy training process. And we see no improve in the autoencoder in both the federated learning approach and the conventional approach, where the model or the data was all pulled together into one point. We were, although, able to see something interesting, is that the conventional autoencoder approach was a bit lesser in results compared to the federated learning plus the autoencoder approach, meaning perhaps that the federated learning was able to mitigate the detrimental effects of having so many different sorts of data with different features at one point, where federated learning was able more or less split it up at one point and aggregate them to be able to handle the difference and have better results in terms of that case. And in this slide, we're trying to reason why we're getting a lower performance despite the cost we paid in training the autoencoder, which is lengthy and a consumative process of training on unlabeled data. Our first assumption is that our model didn't really do well on the UCI client. That's because the UCI client has the least amount of data proportionally to other data sets. So since federated averaging works in a weighted averaging manner, it doesn't really favor uh, clients with low amount of data. And we see that clients with more data is more able to dictate the next generation of the server model that's being aggregated. And the other reason is that there's a high confusion from the SHL client, which is, as you can see here, between the car, bus, train, and subway locomotive classes are often confused with the stand and sit class, which is kind of reasonable, where you can imagine you are sitting and standing in any of these vehicles. But but now the customer has to detect the subtle vibrations or movements of his vehicles, which it's actually not able to do. And even in the unsupervised autoencoder training, standing is often confused with the other classes. So this was a large degree in the decrease in performance since SHAL clients had the most amount of data and clients. And the other reason is simply because the autoencoder feature learning is actually quite lacking compared to more advanced self-supervised learning methods. Here you could see the features or embeddings that's extracted from a real-world client. And we could see that there's not quite a clear-cut separations for the data that's being that the features are being extracted. So we really need something more advanced in the feature learning section, such as the CPC, SimSAR, and MoCo methods, and more. But we need to also adhere to the to the computation and memory limits of on edge devices, which the autoencoder was nice for. And the other and final problem we tried to look into was regarding the orientation and scaling problems of that's happening with feature learning and federated averaging together. We'll look more into it in the next slide. Here, we're looking more into the orientation scaling problems. As you could see here, the circle represents one client and the X represents another client, and the color represents the classes. So here you could see for sitting, good examples, the sitting and standing classes, the green and the red. Client 1 and client 0 are operating in different completely different feature space. So here it's optimizing for client 1's optimizing features for something else, and here another client is optimizing for something else. And if we just combine them together, it's not really, they're not really able to collaborate. So this is a really big issue for federated learning, which assumes that where the clients are helping each other in doing better in their data, but this is actually not the case. So to conclude this study, we presented an invalidated federated learning in a more realistic setting where we consider clients with only unlabeled data, and we try to respect the computation and memory budget of each client in the domain of human activity recognition. Then we try to use the autoencoder based on our assumptions and show that it wasn't really sufficient in capturing or extracting representative, meaningful features. However, we find that the federated learning approach was able to better compensate for the ineffective representations from the autoencoder than the centralized approach. And finally, we showed that our results is exhibits a good study direction for coupling federated learning and self-supervised learning methods that needs further improvement. Here, you may find some of the key reference views for our study. Thank you for your attention. I hope the connection I have right now is good enough for questions if this video is ever played.